Picture a high-performance car on a test track. It launches from a dead stop, holds a steady speed, slams the brakes, and throws into reverse. If you try to calculate the exact distance that car traveled using traditional physics, you run into a serious bottleneck. You have to break the motion down and run a separate kinematic equation for every single phase of the journey. These standard formulas provide isolated snapshots. They spit out a number for the end of a specific time interval, but they cannot show you the continuous reality of the object's journey without endlessly recalculating new variables. Relying on algebra for multi-stage problems is a trap. By translating that same motion into visual geometry, you can evaluate the entire journey at once and solve the problem much faster. The velocity time graph is the central tool for kinematic analysis. It coordinates every major variable of motion by placing time on the horizontal axis and velocity on the vertical. Notice this perfectly flat horizontal line above the time axis. Since the vertical position doesn't change as time ticks forward, it indicates the object is maintaining a constant velocity. When that line angles upward, we get a visual read on acceleration. By calculating the steepness or the slope of this line, we measure exactly how fast the velocity is changing. The angle also indicates direction. If the line drops below the horizontal axis and angles steeply downward into the negative quadrant, the object has a negative velocity and a negative acceleration. It is speeding up, but in reverse. The physical angle and placement of the line provide an instant mathematical read on an object's changing speed and direction. This graph reveals a second property. The physical area trapped between the curve and the horizontal axis represents the total displacement of the object. When the graph dips below the time axis, the space is calculated as negative area. This represents the distance the object traveled in the opposite direction. You can also translate this data into a completely different chart. By taking the slope values from the velocity graph and plotting them as the vertical points on an acceleration time graph, you move down the kinematic ladder. This process works in reverse too. Finding the shaded area under the acceleration graph reveals the net change in velocity. Stepping between displacement, velocity, and acceleration is entirely a matter of basic geometry, specifically slope and area, rather than complex calculus. Standard kinematics focus on the time domain, but some physical forces, like gravitational fields or compressing springs, depend entirely on an object's location in space rather than the ticking of a clock. To analyze these location-dependent forces, we use a chart showing acceleration on the vertical axis against position on the horizontal. When we integrate acceleration over distance instead of time, we find a different relationship. Because acceleration can be expressed as velocity multiplied by its rate of change over position, the area under this curve equals half the difference between the squares of the final and initial velocities. By changing the independent variable from time to space, we unlock a shortcut that determines terminal speeds without ever needing to track the time elapsed. Returning to our car test, the four-stage journey, accelerating, cruising, braking, reversing, is plotted as a single velocity time graph. Instead of algebraic formulas, we fracture the space under the line into basic shapes, a right triangle, rectangle, and trapezoid. Calculating the area of these simple shapes yields the exact total displacement in a fraction of the time required for algebraic substitution. Formulas isolate a single snapshot of a moving object, but graphs map the entire story at a glance. Visual geometry solves what algebraic formulas struggle to represent.